All right, welcome back to part 2 of section 7.3. Here we're going to be looking at some guidelines before we do some examples, okay? So guidelines for proving trig identities. So the first thing you're typically going to do when you're proving an identity is you're going to always start with one side. And usually you're going to start with the more complicated side. So for example, if you look at the very bottom here, number 1, right? You're going to pick a side, and in this case, the left side is actually a little more complicated. So the left side is where we would start, okay? And then step 2 is where you have a lot of different options, okay? There's a lot of different ways you can rewrite the expression. So the first one is you can combine fractions that are being added or subtracted with common denominators. So for example, if you have something like this, right, and we did this in the last lesson, we made the denominators the same. So in this case, I would multiply the first fraction by cosine of b, and then I would multiply the second fraction by sine of a over sine of a. And the whole idea is so that the denominators are the same. That way I can combine the two fractions into one, and I would get something like this. So a lot of times when you see fractions that are being added or subtracted, you might want to make the denominators the same. Next, you might have to factor if needed. And a lot of times you'll know whether you factor or not if you see common factors, maybe a difference of squares, or something that's written in quadratic form. And a lot of times those would be indications of, hey, maybe you should try to factor and see what happens. So for example, here I have sine of theta plus sine of theta cosine theta. If you notice, they both have sine of theta in common, so I can factor out my greatest common factor. I'll be left with 1 plus cosine of theta. In the second example here, this is a difference of squares, which, if you remember, it would become cosine of a minus 1, cosine of a plus 1. So factoring is something you always want to keep in the back of your mind, okay? The next possible option is you might want to split a fraction into multiple fractions. In other words, if you look at this example here, you have sine of a plus sine of b all over cosine of c. And because they're all over a single numerator, what I can do here is I can write this as sine of a over cosine of c plus sine of b over cosine of c. Right? That's one way I can rewrite this fraction. And so the last thing you can possibly do is rewrite everything in terms of sine and cosine. So for example, if I have tangent of x times cosecant of x, and I'm not sure how to simplify that, I might just rewrite tangent of x as sine of x over cosine of x, and then I might write cosecant of x as 1 over sine of x, and then on those, oh look, the sine x's can cancel each other out. I'm left with 1 over cosine of x, which simplifies into secant of x. And so these are some of the different ways that you might have to rewrite an expression, okay? And the last thing you want to do is always keep the goal in mind, right? Because you know what you're working toward. So let's look at a couple of examples today so you'll see what we're doing. So looking at our first example here, we're going to verify this trig identity. So your job is to pick a side to work with, and then your goal is to get to the other side. So once again, you always want to pick the more complicated side. So when I do a problem like this, I'm going to start with the left-hand side. That's what LHS stands for, right? Left-hand side. Because the left-hand side is just more complicated, right? There's more things you can do. So let me rewrite the left-hand side first. It's always good, I think, to write down the side that you're starting with. And then from here, we're going to try to rewrite it using everything that we know. So first thing I would probably do here is just distribute the cosine theta. So if I distribute the cosine theta, I'll get cosine theta secant theta minus cosine squared of theta. And then from here, what I notice is that the secant of theta, I can actually rewrite this as 1 over cosine theta. Keep the second part the same. The reason why I knew that is because I noticed that the cosine thetas would cancel each other out. So what I'm left with is 1 minus cosine squared of theta. Let me just highlight this so you can see where that came from. And then from there, you want to keep going. And you know you want to keep going because this is your goal, right? You know what you're trying to end with. You're trying to end with sine squared theta. And so keeping that goal in mind, I notice that 1 minus cosine squared is simply just sine squared. That's using our Pythagorean identity. And you're done, right? That's your right-hand side. So if you noticed, we picked this side, and we worked with that side until we got to the other side. So you always have to keep the end goal in mind, because sometimes what's going to happen is you're going to get lost along the way, it might be a good idea to look ahead and to figure out what you're trying to get to, okay? Let's look at a couple more examples together just so you can get an idea of how these work, and then I'll let you do a couple on your own as well. So looking at number 2 here, I have cosecant to the 4th minus cosecant squared of theta equals cotangent to the 4th theta plus cotangent squared of theta. Now, in this case, I don't think there's really a wrong answer here to go from the left side or to the right side. So for this one, I'm just going to start with the left-hand side. So starting with the left-hand side, I'm just going to rewrite the left-hand side. And then from here, what I notice is they have cosecant squared in common. So I can actually factor that out. So when I factor out a cosecant squared of theta, I'm left with a cosecant squared of theta minus 1. So hopefully you'll notice this cosecant squared of theta minus 1, and you'll think, hey, I can actually rewrite this using one of my Pythagorean identities. Now the Pythagorean identity that you want to be using is that cotangent squared of theta plus 1 equals cosecant squared of theta. Because from there, do you notice that if I subtract 1 from both sides, I'll be able to use the fact that cosecant squared of theta minus 1 is really just cotangent squared of theta? So from here, I can rewrite this as cotangent squared of theta. And again, I'm just highlighting these so you can tell that these are the exact same, right? And that'll be my next step. Now at this point, I'm kind of stuck because I'm looking at what I have and I'm wondering, how the heck am I going to end up with cotangent to the 4th of theta plus cotangent squared of theta? So a lot of times you might have to pause along the way and just kind of think about what you have and what your goal is. Now the fact that I have everything written in terms of cotangent though gives me an idea. It tells me that I have to do something with this, right? Because the only trig function I want to see in my final answer is cotangent. So the question now is, how do I get rid of this cosecant squared of theta? And if you noticed, we used this identity already, right? And if you notice, I can just use it again. This time I can just replace cosecant squared of theta with cotangent squared of theta plus 1. So in this case, let me just use a different color here. I'm going to be replacing cosecant squared of theta with cotangent squared of theta plus 1. And again, this is just using my Pythagorean identities. And then from there, I'm still looking at my end goal, right? Because this is my goal. I'll notice that, hey, I just have to distribute the cotangent squared and I'm done. And this is my final answer, right? I started with the left-hand side and I ended with the right-hand side. That's the way to do it. You never want to meet in the middle. And what I mean by that is you don't ever want to work on the left-hand side and the right-hand side until you get to a point where they're the same. You have to pick one side, commit to it until you get to the other side. So hopefully you get an idea of how we're using these identities, right? Typically, whenever I see something being squared, I'm always going to be thinking of the 3 Pythagorean identities, though, a lot of times. More often than not. So this is the general idea of how to prove trig identities. You're starting somewhere and you're ending somewhere. The question is, how do you get from here to there, right? You know the destination and you know the starting point, but you don't know the path to get there, right? I think of these kind of problems like a maze in that sense. So that's why I like this section, by the way. I think this is just fun, if I can use that word. But anyways, let's look at another example. So I'm going to actually do number 3 as well as number 4, just so you can kind of just follow along. And then I'll let you do a couple on your own eventually, okay? So starting with number 3 here, again, you want to assess your equation and you want to think which side looks more complicated. Now, I think it's quite obvious that it's the left-hand side that's a little bit more going on. So we're going to start with the left-hand side again. As usual, I would recommend you rewrite the side that you're starting with. It's just good form. And our goal is to get to cosine squared of a. So keep this in mind, right, as you're doing this problem. So from here, I think, okay, what can I possibly do here? I feel like you can break this up maybe into 2 fractions. You can maybe use some sort of Pythagorean identity. And I feel like it's the Pythagorean identity route that we're going to be using. And the reason why is because I'm looking up here. I'm looking at this cosecant squared of a minus cotangent squared of a. Because this just comes from one of the Pythagorean identities, right? And the Pythagorean identity here is cotangent squared of theta plus 1 equals cosecant squared of theta. But in this case, I'm just going to subtract both sides by cotangent squared of theta. And if I do, I end up with 1 equals cosecant squared of theta minus cotangent squared of theta. So in other words, the numerator is just 1. So see how I got that, though, based on my Pythagorean identity, right? The bottom still stays the same. And then from here, again, I'm looking at the fact that I'm trying to end up with cosine squared of a. And I realize I'm done here, right? Because 1 over secant is just cosine. So 1 over secant squared of a would just be cosine squared of a. I'm good. So hopefully you kind of see how we did that. Let's look at number 4 together as well. Now number 4 is, I'm going to throw in a strategy that we haven't talked about yet, but it's something that you want to keep in the back of your mind. In this case, I'm going to also start with the left-hand side, okay? So the left-hand side is just cosine of u over 1 minus sine of u. Now for a problem like this, one thing that you cannot do is don't write this by the way, you cannot break this up as cosine of u over 1 minus cosine of u over sine of u. This is just incorrect. You only can do that when the denominator has a single term or is a product of terms, right? Anytime you see a sum or difference though in the denominator, you can never break it up like this, okay? And so what we're going to do here is we're going to multiply the top and bottom by 1 plus sine of u. Essentially, it's a conjugate of the denominator. Now you're probably wondering, how the heck would I know that? You wouldn't have known that, but now you will, because I just showed you this. But let's look at what happens when we do this, okay? So this time I'm going to distribute the top and the bottom, okay? So if I multiply the top out, if you notice, all I'm doing here is I'm distributing the cosine of u. So if I distribute the cosine of u carefully, I'll get cosine of u plus cosine of u sine of u. On the bottom, if I multiply that out, it would be a difference of squares, so I'll just end up with 1 minus sine squared of u. Feel free to follow that out just to verify that this is what you would get. So at this point, what I would do next is I would notice that this denominator, this 1 minus sine squared of u, I can actually rewrite that using one of my Pythagorean identities. Keeping the top the same. The bottom will become cosine squared of u. All I did here was use the fact that I know that sine squared of theta plus cosine squared of theta is equal to 1. So if you notice, if I subtract both sides by sine squared theta, I'll get that. And so from here, now I'm going to break this up into 2 fractions. And part of the logic behind this is because when I look at my final answer, I'm left with 2 separate terms, right? Something plus something. So that tells me that when I have this fraction here, I want to break it up also into 2 separate terms. And so now in this case, I can actually break this up into 2 fractions. I'm allowed to do that here because if you look at my denominator, it's just like a single term that's being squared, which is fine. As long as there's not a sum or difference on the bottom, I'm okay. From here, I notice that I have cosine of u over cosine squared of u. So I can divide a cosine of u out, and I'm just left with 1 over cosine of u. I could do the same thing on the other side. And if I do that, I'll be left with sine of u over cosine of u. So again, I just divided out a cosine of u. So looking back, I probably didn't have to distribute this cosine of u, right? If I just left it alone on the outside, I could have just simplified that out with one of the cosine u's on the bottom. So sometimes you'll notice that, oh, maybe this wasn't the best way to go about it, but now we know. So from here, what I noticed though is that 1 over cosine of u is just secant of u, and then sine of u over cosine of u is just tangent of u. And that's my right-hand side. So this is why you always have to look at your goal, because if you don't, you might get lost, right? So a lot of times the goal will give you an idea of what you're working towards. So keep that in mind. So this is the idea of proving trig identities, right? You're just rewriting expressions, you're using all your identities, and you're doing a lot of simplifications, right? You're adding and subtracting fractions, you're dividing things out, you're factoring, and things like that. So be very careful because there's a lot going on here. So at this point, I'm going to let you guys try number 5 on your own. Again, be very strategic here when you're picking which side to begin with. Pause the video, and as usual, when you're ready, press play. I'm going to start with the right-hand side for this one. A lot of times when I see fractions, I'm usually going to start with that side. And so the right-hand side will be 1 over 1 minus sine of x minus 1 over 1 plus sine of x. And just like we did before, I see 2 fractions that are being added up. I want to make them the same denominator. So the way we're going to do that is we're going to multiply the first fraction by 1 plus sine of x to the top and the bottom. And then I'm going to multiply the second fraction by 1 minus sine of x to the top and the bottom. Hopefully you see why I did that, because I want the common denominator to be 1 plus sine of x and 1 minus sine of x, right? Now from here, we're going to just simplify it out, okay? On the top, I'd be left with 1 plus sine of x. I'm going to actually multiply the bottom out. If I do that carefully, I'll get 1 minus sine squared of x, just difference of squares, minus, now for this fraction here, the top will just become 1 minus sine of x, and the bottom will again be 1 minus sine squared of x. Now from here, I'm going to combine the two fractions by subtracting them. Now be very careful for this step right here. I know the denominator doesn't change. Now for the numerator, I'm going to break this up into two steps. I'm going to take 1 plus sine of x, which is from the first fraction, and I'm going to subtract it by the numerator of the second fraction. Note that I put parentheses there, and the reason why is because that's going to remind me that the minus sign has to distribute to everything there. Now if you carefully distribute the minus sign, you'll be left with 1 plus sine of x minus 1 plus sine of x all over 1 minus sine squared of x. If you notice, the ones will reduce each other out. So you're left with sine of x plus sine of x on top, which is just 2 sine of x. Just so we're clear, these ones will cancel each other out. And then the bottom will be 1 minus sine squared of x. Now from here, what you need to notice is that 1 minus sine squared of x is just cosine squared of x. We're using that Pythagorean identity again. Right, this is the exact same thing as this. And then from here, I'm going to do a little manipulation. So at this point, I'm going to actually look at my goal. My goal is to get to 2 tangent of x secant of x. I'm looking at what I have. I see a 2 there, so that's looking good. The question is, how do I get tangent of x and secant of x? Well, what I realized is I can actually rewrite this. Isn't this really the same thing as 2 times sine of x over cosine of x times 1 over cosine of x? Right? Do you agree that's the same thing? Now, isn't sine of x times cosine of x just tangent of x? And isn't 1 over cosine of x just secant of x? That's what we're trying to get to. We're done. This is our answer. Now, the thing about these Pythagorean identities is that there are more than one way of doing it. So you might have got the same answer without doing it the way I did it, and that's totally fine, right? So that's number 5. Hopefully you're able to get that. If you didn't, that's okay. You're going to have some multiple opportunities to practice. So at this point, I want you to try number 6 on your own. Think about all the different strategies, right? Look at the guidelines if that helps, and then try number 6 when you're ready. Now for number 6 here, I'm going to start with the left-hand side. Just because, again, it's more complicated. So the left-hand side is cosecant of theta minus cotangent of theta all over secant of theta minus 1. And just like before, we need to think, okay, what should I do here? Now for this particular problem, I'm going to write everything in terms of sine and cosine, right? That was one of our strategies that we could use. So if I do that, let me write this giant fractional sign. So cosecant of theta is just 1 over sine of theta minus cotangent of theta is really just cosine of theta over sine of theta. On the bottom, I can write secant of theta as 1 over cosine of theta, and then the minus 1 just stays the same. Now from here, what we have is a complex fraction. We have a fraction within a fraction. And so the way I'm going to do that is I'm going to just do these one at a time. So what I mean by that is I'm going to first start with the numerator here, okay? If I simplify just the numerator, do you notice that they have the same denominator? So I can combine those into one fraction. I'll be left with 1 minus cosine of theta over sine of theta. And that's going to be that. Now what I'm going to do next is I'm going to take the denominator and I'm going to combine that into a single fraction. So to do that, what I'm going to do is multiply the 1 by cosine theta over cosine theta. Because now that they have the same denominator, this will just become 1 minus cosine of theta over cosine of theta. And at this point, I have a fraction divided by a fraction. What I can do is rewrite this. I can take the numerator and I can divide that by the denominator. And if you remember, when you're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So really, I could just multiply this by cosine of theta over 1 minus cosine of theta. And from there, hopefully what you notice is that, hey, I can reduce these 1 minus cosine thetas out. And if I do that, I'm left with cosine of theta over sine of theta, which is just cotangent of theta. And that's what my goal was, right? My goal was to get to cotangent of theta. Hopefully you're able to get that right. If not, no big deal, right? Because this is not a simple concept. Hopefully you're getting a hang of what we're doing here. Just a lot of different ways to rewrite things, right? A lot of properties that we're using. So we're going to be looking at 2 more examples here. As usual, I want you to try number 7 on your own. Do your best. Pause the video, and when you're ready, press play. For number 7 here, I'm going to be starting with the left-hand side. Again, it's more complicated. I'm going to just rewrite this for now. And so from here, I need to think, okay, what can we possibly do to rewrite this? So the first thing here that I notice is that this is one of my Pythagorean identities, right? That's just cosecant squared of theta. So what I'm going to do is rewrite that first. So cosecant squared of b, sorry, not theta. And I'm just highlighting these so you know these are the same. And then from there, what you can do next is you can actually rewrite this. The way I'm going to rewrite this is I'm going to break this up into multiple fractions. So in this case, I can break this up as 1 over cosecant squared of b minus cotangent squared of b over cosecant squared of b plus, and then this last term is going to stay the same. Now from there, I notice that 1 over cosecant squared is really just sine squared of b. And then let me just keep everything else the same for now. At this point, my main focus is going to be on this term right here. I feel like there's a lot I can do with that, right? I want to be able to simplify that. I think the way I'm going to simplify this, though, is just write everything in terms of sine and cosine. I feel like that's going to be a lot easier. So keep everything else the same for now. So when I see cotangent squared, let me move this all down. When I see cotangent squared, I'm going to rewrite that as cosine squared of b over sine squared of b. And when I see cosecant squared of b, I'm going to write that as 1 over sine squared of b. I'm going to keep everything else the same. Now from here, I'm going to keep the sine squared of b alone. Now, in this case, I have a fraction divided by a fraction. So really, you can think of that as take the numerator, and you're going to multiply it by the reciprocal of the bottom, and keep everything else the same. And if you notice here, I have cosine squared over sine squared times sine squared of b. The sine squares cancel each other out, huh? And what I'm left with is sine squared of b minus, now this whole thing right here just becomes cosine squared of b, right? After everything becomes simplified. And then plus 2 cosine squared of b. We're getting close. If you notice, you can combine these together, right? If I have negative 1 cosine squared of b and I add 2 cosine squared of b, I'll have a positive 1 cosine squared of b. So this will become sine squared of b plus cosine squared of b. And if you notice, this is your Pythagorean identity. This is just 1. And that was our goal, right? Our goal was to get to 1. That's your answer. So a lot of times, you're going to have to stop along the way and pause and think, what am I going to do next, right? I'm only able to go through these pretty quickly because I've done hundreds, if not thousands of these. And so it might take you a little bit of a while in the beginning, but don't be discouraged by that, okay? Just persevere through it, right? Think strategically, keep reviewing your identities, and figure out what you can possibly do next. Here's our last example for today. As usual, try number 8 on your own, and when you're ready, press play. So I'm going to definitely start with the left-hand side here. And then from here, I'm thinking, okay, is there anything I can do with this expression? One thing that kind of catches my eye is the secant squared minus tangent squared. Because anytime I see like secant squared, tangent squared, sine squared, you know, those kind of functions that are being squared, I think of the Pythagorean identities. And secant squared minus tangent squared is actually just 1. And the reason why that's true is because if you remember, you have 1 plus tangent squared of theta equals to secant squared of theta. If I subtract both sides by tangent squared of theta, I'll get that. Now from here, I have 1 plus tangent of theta over secant of theta. It's looking a lot nicer. The next thing I'm going to do is I'm going to break this up. I'm going to break this up into multiple fractions. I'm going to write this as 1 over secant of theta plus tangent of theta over secant of theta. If in this step you wrote everything in terms of sine and cosine, that is totally fine. as long as you do all your work correctly, you'll get the right answer too at the end. But here I'm going to break it up. When I see 1 over secant of theta, I notice that's just cosine of theta. Plus, now tangent of theta over secant of theta, I don't know what that is. So what I'm going to do there is I'm going to write that in terms of sine and cosine. So tangent of theta is just sine theta over cosine of theta. And then secant of theta is just 1 over cosine of theta. And then from here, I'm going to rewrite this further. So I have cosine of theta plus, now in this case, I'm going to take the numerator. And once again, because I'm dividing by the denominator, that's the same thing as multiplying by the reciprocal. And just like before, the cosine theta is here. You notice they'll cancel each other out. And what I'm left with is cosine of theta plus sine of theta. The last step is just to write it as sine of theta plus cosine of theta, and I am done. This is called proving identities, right? Proving trig identities. You're starting with one side. You're going to be using all your identities and all the different ways of rewriting an expression, and your goal is to get to the other side. Hopefully you get an idea of how to do this, but I think the best way to learn this is by keep practicing. So review your identities, do your homework, and hopefully you'll get better at this. And hopefully this is something that you enjoy. If not, at least understand how to do. So guys, this is the end of 7.3. We only have one more lesson after this, so hang in there guys, we're almost done. Alright guys, have a wonderful rest of your day.